Welcome to our LMI webinar series. Today we have with us Marion Sitko, Field Application Engineer at LMI, and Edwin Popp, Global Account Manager in LMI, who's also an expert on EV battery inspection, which is what we will be discussing today. So just a few notes before we get started, and I hand it over to Marion and Edwin. This webinar is being recorded, so if you need to leave for any reason, you can watch this later. About 2 to 3 hours after the webinar, you will get an email with the recording. So just keep an eye out for that, and if you don't see it, check your spam folder. On the right-hand side, there is a chat function. So if you have any questions during the presentation, please put them in the chat, and we will do our best to answer all your questions. And we will answer the questions at the end of the presentation. So if we don't talk about it in between, there's a reason. But without any further ado, Edwin, take it away.
Okay, good day, everybody. As Vanessa said, my name is Edwin Popp, Global Account Manager, and we will talk today about the 3D inline inspection solutions for the EV battery manufacturing. So, but first of all, we have a quite big audience already. Maybe not everybody knows about LMI, who's LMI, what we are doing. A brief introduction. We are a company specialized in 3D inline sensors or inline inspection systems, located in Vancouver, Canada. So there is our HQ. There we develop, produce, calibrate, and actually send every sensor out. What you see there also in the map, on the map, we do have 12 regional offices worldwide, 5 in North America, 2 in North America, 5 in Europe, and 5 in Asia. And we also work with more than 60 distributors in more than 40 countries around the world. This we mark with the yellow spots, what you can see. So we are actually worldwide available if there is a need. All right, so we do have 4 types of sensors or 4 types of technologies what we provide as a solution. The first one is a simple displacement sensor. If you move the target below, you will get a profile and you can inspect the profile. We do have the line profilers. That's our, let's say, major part, because we do have a lot of several different sensors regarding accuracy, speed, and field of view. So you get straight a profile based on the triangulation technology, and if you move the target, you will also get a 3D image. The third technology is our snapshot sensor. Snapshot sensor means it's just the opposite. The product has to stay, and we take a snapshot with a few milliseconds, and you get directly the point cloud, which you can analyze. And our newest are the focal specs. So those are the LCI sensors. It's a patented technology what we have. Just a brief, what's the difference about that or of those? We can scan with those sensors any kind of material, so it doesn't matter is it glass, transparent, or matte, or dark. We do have a maximum accuracy, or it goes down to 100 nanometers, and we do have a resolution in X direction of 2,480 points. So it depends on the measurement range. It goes down to 1 or 2 microns. Scan rates from 3 kilohertz up to 16 kilohertz is possible. And as I mentioned before, doesn't matter what material, this sensor can scan every surface, also mirror, and you get brilliant data, good point cloud, which you can analyze or do several measurements on those. So the another, let's say, important part is that if you get a sensor, you have a cable there, and within this sensor, you also receive directly the software. So the built-in measurement tools are already included in the sensor. You can easily, by drag and drop, that's what you see on those 2 images. It's simply a window. You place it there, put some parameters into it, and you directly receive a calibrated measurement. It's kind of small right now in this presentation, but you see directly the gap, or below you see the depth or the flush of this measurement. And this is all included. You can use a PC, but you don't have to. So now we're gonna start with this, with the 3D inline inspection technologies and the solutions what we have, or where we are working, still working, or we already also realized several of those projects, and we try to make an overview, or in this presentation we go through the whole process of battery manufacturing. So the whole production line, we try to put it in, or to cut it in parts where our sensors are beneficial, and where we have some material what we can show. So generally speaking, usually if you start with the production of a battery, you start with a coil of aluminum foil or copper foil. So you start with coating and drying. Then below you see the calendering. Then up on the right side, you cut it into the right size electrodes. Then you assemble the cell. You do the battery welding, so you have the full battery cell. And if you after this, you combine those cells into modules or battery packs. And as you see already here in those parts, everywhere there is some need, or also some benefits which you can provide with these sensors. Let's start with the cell production. As I mentioned before, you have a coil first. This coil, if you unwind it, it has to be cutted. So in the middle stripe, you see there are some tabs on the left side. Those they get cut out, and afterwards you have to separate those to get the electrode size. And during the process, or during the production, those knives, they can wear off, and so the cut itself is not that clear, and you can get some burrs. This is I draw it with the red triangle. So those burrs, you never know how they're sticking out. They can stick out from the top view to the side, or up or down, depends on the cutting process. Those burrs, they're pretty small. We're talking about a few micrometers only. But they are very important to detect, because those can be a safety issue in the product life of a battery, because they can pinpoint the insulator between the electrodes, and well, this leads into a malfunction of the battery, or in worst case a fire or explosion. So this is also very important to inspect. What we did, and that kind, you see now on the left side again the image, but this is now, I put the black area. This is the coating. So it can be also checked while after the coating. We did a scan of some samples, what is here on the right side, with our LCI sensors first for burrs, but also in that picture you see that we check the after the coating directly. So the position or the offset of the coating compared to the edge of the foil, or also the thickness of the coating, how flat it is or how even it is. And important is also the continuity in X direction, but also in the production way, that we don't have some waviness. So it's actually a typical application what you have also in the printing industry. It has to be a flat, even coating. Results of that are looking like this. So we have on the top, you see that's a copper foil with a coating, and there's a good coating. So it rises slowly, and then you have a nice even thickness of the coat. And below, that's one of those issues which can happen. You see the edge, and on the edge it's a bit higher and not that smooth, the coating, and then in the end it drops a bit, and then you have a smooth surface. This is just if you have a continuous coating on the sides, this may happen, and this also directly leads into a worse quality of the battery cell. And with our images, you directly see, okay, that's just a visualization, but you can measure straight if there is a difference, or if you have to interact into the process. This is now an example. Before there was a continuous coating, but there is also a production of pattern coating. Pattern coating means you have interruptions between the coating processes. You see there where we put the measurements in. It's the start of the coating of the pattern, and there it always happens that you have much pressure, and so the start of this coating, you have the same like before, you have a little bump, and then it drops down, and then you have the evenness. This is something also where, yeah, it depends on it's just quality issues, what can happen. And in parallel, we are also checking the offset of the edge of the coating to the edge of the foil. And what I try to explain right now is that here in the profile, you see that there's the foil, you start coating, and then you get this drop. In this case, it was 0.057 millimeters high, but then it goes down to 0.024 millimeters, which is the right side of the thickness of the coating. So the next application is, well, the cell assembly. And Marion will take over from that point.
Thank you. So yes, the second part after the cell production is the cell assembly and its inspection. So the placement of the top cover must be precise on the battery shell before welding. If the gap between the edges is greater than a certain size or the parts are not flush, the quality of the weld and the quality of the entire battery will be compromised. This is something challenging to measure with 2D because with 2D you can get the gap, but you cannot get the flushness. For the flushness, you need the high data, the point cloud. The fit tolerance between top cover and shell should be verified to ensure that the sealing welding quality meets the requirements after the press fit of cell. So for this application, we will mount a Gocator 2520 on the top of our battery to generate the point cloud you are seeing on the picture. Then, with the onboard tools of the Gocator, we can measure the gap and flush directly on the Gocator. You can also give to the Gocator the tolerance you have for gap and flush so that the Gocator will only send you a good or not good signal at the end directly on your PC or PLC via different protocol like Profinet, Modbus, ASCII, Ethernet IP, depending of your needs. Then, once the assembly is done, comes the cell assembly weld inspection. Once the laser welding of the battery cell is complete, the quality must be verified. Here we are looking for defects such as overflows, breaks, and openings like you can see on the picture in the seam. We could inspect it manually, but this would be time-consuming and would slow down the production a lot. We could also analyze it with 2D, but to meet the needed resolution, it would be quite challenging. So for this application, we will mount two Gocator on the top of our battery with a 45-degree angle. Both connectors are network. It means that they are working in a buddy system. And at the end, we will get a single point cloud of the entire weld seam. Then we will use the onboard tools of the Gocator to analyze the quality of the weld seam. First, we use surface blob to isolate the weld seam of the rest, and then surface track to analyze the quality of it. Surface track will return us along the weld seam the height, the width, the continuity, and the volume of it. The laser welding process may cause some kinds of defects such as bump, dents, pinhole, burst hole. So if we mount a Gocator 2520 on the top of the weld, we can check its quality as we've seen before, but we can also guide the welding process in real time with very high accuracy and very high speed. Here are some types of defects we are looking for: welding burst, polarization, bump. On the top, you have the height map of the default, and on the bottom, you have the intensity picture that we also get with the Gocator. Depending on the default, we will use one or the other. Other example, slag, burr, black spots. Another welding inspection is also done on the connector. We will use the onboard tool to be sure that the quantity of weld is enough for a good connection. For that, we will use surface volume to measure the volume of the weld. Then we will check the position of each connector relative to the size of the battery. For that, we will use the tool Surface Edge to detect all the edges of our battery. And then we will use the tool Surface Blob to detect each connector and its position. We will finally combine the result of both tools to get the position of each connector relative to the size of the battery. The Gocator, and especially the Gocator 2500 family, is able to generate a very high precision point cloud thanks to its very good sensitivity and blue laser, even on highly specular surfaces like metal weld seams. And then I give it back to Edwin.
Now you can hear me. Okay, so let's say the next part of the process, the cell features inspection. So after welding, we do have the full cell, and we need simply, in that case here, we're checking the surfaces. The battery cell has 6 surfaces, and most of them are well, very important. Here on the left picture, you see that's our lab unit, lab setup, just with a simple one sensor on the top, and the battery is going, is driving below. We scan this area, and on the right side you see one terminal, and that's very important to to check those for the parallelism, the scratches, and also simply, when the parallelism depends on both terminals, or we call it here the pole pillars, that they are even to each other, or parallel, simply saying. In that case, what we do, we have 4 windows on each corner of this terminal, and simply creating the plane and checking those 4 planes to each other, and also then, of course, we're comparing those planes to the planes of the other terminal side. Now, this is another surface. What can happen is also due to production or handling of those cells, they can have some scratches. Those scratches, visually, you as a producer, you don't want to provide those products with scratches to a customer, of course, but also on the technical side, those scratches, if they are deep, they can also bring a defect, or simply decrease the quality of the battery. And in that case, what we see here, as Marian mentioned also already before, we do have the intensity image and the in the 3D data. That's a pretty big advantage, because some issues or some features you can't detect in one or the other image, but with both we have always the chance. So we have this advantage that we can check for both, and in one of those we will find a defect. So in the upper, you see it's more whitish, it's coming out, and below you see, in the 3D image you all see the scratches. What we do there on the right side, the same as before in the terminals, just with 9 points, we check the flatness of this area of the battery cell, and what you see is that there is a difference. You have a little bump in the middle of this window. That's also very important. Those cells, they breathe kind of while charging and discharging, so it's always like it's extracting and also it's going thinner. And for the packaging size in the next production processes, this is also very important to inspect if that's also within tolerances. This is an example. It's actually before, so this is after the stacking. So you have the electrodes and they stack together. And on the left side on the picture, you see those 2 tabs. Those tabs, those are all the electrodes stacked together. They have to be soldered together. This happens mostly by ultrasonic welding machines, and if those are not pretty soldered, or if there's going something wrong, you can get cracks, it can break, or simply if it's not properly welded, the electricity flow is not can be different than as usual of this battery cell. So this is why also that is important to inspect. So we simply use for that is again the 25 series of our Gocators, scanning those, and what you see on the left on the two right images, how those welds looked like, and this is a bad weld because you see it's not totally welded, or not fully welded. Afterwards, so if you have the full cell, you welded the lid on the top, what Marian presented before, you have to fill the electrolyte. For that, you have this liquid injection port, so it's between the terminals. You have those two features. The first one, or what you see on the left picture right now, is the liquid injection port. If you filled in the liquid, you have to, well, close this with a rubber plug and put a special nail into it and weld. So it's kind of like a sealing of this area, that the liquid can't be poured out and nothing else can get in. For that reason, we used our LCI sensors simply to get a high density of point cloud. What you see on the right side, that's a scan of those, to simply inspect for pinholes. So actually the same weld inspection as before with the lid and shell. What we did, we do it simply on this injection port. So it's a similar, let's say, from the vision perspective view, it's the same application, but in the production of a battery, it's a totally different environment again. Right next to this injection port, we see this explosion-proof valve, which also, it is a safety feature, so it has to be inspected and checked that it's mounted or that's produced right, and that also the safety is given. Because if there is a malfunction, this is the place where it where it pops out or rips, and not the whole battery will explode, for instance. In that case, you see on the top image, that's a good product. It's nice flat, and below you see there can be some caulking on the edge, so it's some kind of like upper lift, not closed properly, or you simply have some pits or some gouges, which shouldn't be there. The same we did also with our with the Gocator 25 series. So on the right, on the left side, you see we scanned after this the pit hole. We scanned the valve, simply also to provide this image. And what you see there is similar. So before was with the LCI, also with the Gocator, we are capable to check that. So we do have different technologies, and it depends always on the application and the needs. Both can handle several applications. All right. If the cell is fully done, we need also to check simply the dimension of the cell. As I said, the cell has to breathe, so it has to be within tolerances. And in this setup, what we did, it's also in our lab. You see there are three sensors. What we set it up. So one on the left side, on the top side, on the right side, and the cell in the production line. The cell's usually going one line direction, so they simply driving through, and those sensors scanning the cell, and you create the 3D image what you see on the right side. In one project in Germany, we used actually 6 sensors in a reversed mode, simply to get also not only those 3 surfaces, so left, right, top, also the front and the back. So we had to angle them in a special way, and just by driving in one direction, we could inspect all 5 surfaces, except the bottom surface. If the cell got inspected usually before the cell gets some insulation around itself. So there is either it gets painted or sprayed on it, or also there is a foil it simply gets wrapped in foil as insulation. Before this wrapping or painting, it's very important to check if there are any particles on the cell. This is something what I got a few requests already that customers needs to check that. Simply, if there is a particle in between, like in the beginning with the burst I explained, it can happen that if there is some particle in between two cells and it rubbing through the battery lifetime, it can rub through the insulation and, well, get also short circuit. In this example, you see now simply bubbles, so it's wrapped but not in a good way. So you have simply some bubbles between, below the foil. Which that's just an example, and what we see on the left side is just with one sensor what we did from the top, but you can imagine in production, in a one-way production, we need to use 3 or even 6 sensors to simply inspect all sides in one way, because this battery production is also very fast production, so you need to be quick, and that's also what we can reach with our sensors with a high scanning rate. If we go further, this is how it looks like. We do have those bubbles. We can put, that's one method, simply put a section on it, and then you have the profile and can check for the height or the thickness. The same way we are inspecting for dents, because through handling processes, those battery cells, they can get some dents from the side. Same here, it doesn't look good, and for the customer, but it also it depends how deep this dent is. It can be also some can be some issues in the quality of those batteries. It's just the different way. So instead of a bump, you have, of course, a valley. That's just an example to show that we can not only measure big bubbles, 0.6 millimeters, they can go down actually, or we can detect down to 1.1 millimeters of height or depth. And if it goes below that, 50 microns is also possible, but then we need also a different size, a different sensor. And with the different sensor, you have a smaller field of view, so you need also much more sensors to inspect the full area of the battery. So the other method is using a blob tool. It's also a built-in tool within our sensors, which simply analyzes the full scan surface, and it detects those blobs. You see they are marked, and based on the marks, you can get also the area. So in square millimeters, for instance. That's important because sometimes if you have a dent or a bubble, it doesn't matter which it goes up or down, but sometimes if the depth is all right, but maybe it's pretty big dent or pretty big bubble, it can affect the further processes, or also, as I said, the quality of the battery. So we are using both of those tools instantly or parallel to inspect for those features. Another issue is simply if you wrap it in foil while handling, you can rip or tear off a piece or part of this foil, and then you have an opening there. The foil is pretty thin, but still, as you see here, that's a scan or the scan example. We can detect that, so you see this on the right picture that the foil is teared off and it just flipped over on the other side. This is also next to dents, bubbles, particles. This is also an issue which can happen. So in the next step, it will be the pack assembly, and Marion will take over from here.
Thank you. So yes, we will finish with the module and pack assembly inspection. So here again, when we did the final assembly of the module, we will have a weld inspection. And here we are looking for defects such as overflow, offset, cracks, burst holes, and hair holes. So we will put Gocator 2520 on the top of the weld. And here again, we will analyze those defects with the 3D high map or with the intensity picture, depending on which defect we are looking for. The next weld inspection is the one of the bus bar. So here we will inspect the quality of the weld and as well as the height and the gap between bus bar and pole to be sure that the location is the right one. So we will combine several tools like surface edge, surface volume to be sure that we have enough welding to get all those information directly in the Gocator. Then come the module glue inspection. So the assembled module needs to be installed using a glue bead inspection. During this process, we will get the height, width, and continuity of the glue, again with the onboard tool surface track. So we will get that continuously, and this will ensure us that the bonding is strong and secure. At the end of the inspection, we will use the Gocator a last time to get a point cloud of our entire module. So you can see in the picture, you have the module in the middle, and around the module, you have several Gocators. So we will build a multi-sensor setup again to get a single point cloud of our entire module. Then we will measure the height, the width, and the length of all the faces, and we will also control the flatness of each faces to be sure that all dimensions are matching the GD and T design tolerances. If not, the battery will be rejected. For that, you can use the Gocator 2530. Once we have our battery, a battery cooler could be needed. To inspect it, here again, you can use the Gocator, for example, to inspect the flatness of the battery cooler or to check some key points. We had an application, for example, where we were looking for both holes in the point cloud you can see. So we use the tool surface holes 2 times to find the location, the precise location of both holes. And then we mix the result of both tools in the tool feature dimension to get the distance between both holes. And here again, we put the tolerances directly in the Gocator so that the sensor can directly send a good, not good signal without any PC. So thank you for watching. And now we will have a look to your questions.
I would like to add for the last application, this is just a little part of this piece. You know, usually you have the whole battery, the whole battery, not the pack, but what's called in English? That's a good question. Wanne.
The tray.
A tray, yeah. So it's bigger than 1 meter width, or in 1 by 1 meter, for instance. So it's a lot of data what you have to acquire for to check the positioning of those inserts, because usually it's automatic process. A robot picks it and then put it on, so it has to fit directly without any issues, and that's the background, I would say, or that's a target why we need to inspect those as well. And also the flatness. It's metal sheet, so it can be bended, pre-bended a little bit, and during the automation process, it has simply to fit directly while mounting.
Okay, great. Well, let's go through some of these questions. The first question is, can you explain again the use case for the focus spec LCI? When do I have to use one? Or when is like a normal line scanner better?
Okay, that's the question from Christian Graf. Yeah, so it's kind of hard to say. Those are totally different technologies, but I would say I would always try first with the Gocator, because it's a smaller volume of package size what you can use, and you can combine several Gocators together, you know, to do a ring layout or a body mode, so up and down or left and right to measure the thickness. And if it's not working with those, then the LCA I would say might make the job better. The biggest difference is simply if it's very shiny or it's glass and mirror, then the LCI is simply, that's the way to go.
Okay. We got lots of questions, so I'll try my best to work through them. Which tool will be used for defect inspection? What will be the time requirements to train for tools? But let's start with the first part of that. Which tools will be used for defect inspection?
So it depends on the defect we are looking for. As we said, for the weld inspection, for example, you can use a tool surface track because it gives you all the information you need. Sometimes you will also work in profile and not surface just to get the gap and flush or to get the height of the weld. Yes, so it really depends on the defect you are looking for. And also, as we mentioned, we also have the intensity picture. So sometimes we will work with the 3D height map. Sometimes we will combine the result with the result we are looking for on the intensity picture. Yeah, and what will be time requirement to train tools? You only have to do it once at the beginning. It's very easy. So I don't know if you ever used the Gocator before, but we try to make our tool very simple that everyone can use them, even if you are not a vision specialist or if you don't program at all. You don't need any programmation. Everything is drag and drop. So, and if you need time to configure the tools, of course, we can help you. You can still send us some support file with a point cloud on it, and we can help you and give you some advice how to configure the tools and which tools you should use.
Okay, great. The next question is, how is the setup working within a welding cell, let's say with a laser welding setup? Do you attach the camera to the welding head or off-axis mounting?
It depends if you are able to protect your sensor from any projection. So the key is really to protect your sensor so it doesn't get break, but you can do both.
Yeah, I would also say it depends on the environment and what cell it is.
But of course, our team will be happy to check your application and see what would work best for you.
Sure.
Yeah. So regarding the checking of the dimensions of the cell, is it necessary for the object to be at a standstill, or could you move the object through the field of view of the sensor?
So you need a movement. It doesn't matter if your sensor is moving or your part. So you could also have your sensor not moving and the part moving through the field of view of the sensor.
Also, in the battery industry, what I saw so far is it has to be fast. So they don't like to be stopped or to have to stop to have a stand time. So it's really in continuous production. So that's actually a no-go if you have to stop somewhere. It has to be on the move.
Okay. How do you detect the scratches and wears on the cell surface? What measurements tools are used?
So we can combine here again several measurement tools. It depends on the side of the scratches. So sometimes we go with a surface blob. This one gives us very good results. If we have a more precise location when we are looking for the scratches, we can use a surface section combined with profile tools. Yeah.
Okay. Next question is, how will the polarization be visible in the 3D point cloud?
For polarization, I think we will more use the intensity picture than 3D point cloud. And then we will use surface blob on the intensity. But yeah, I just want to make sure that it is understood. We can combine both. So we can combine in one scan directly. We can look for defect in intensity picture and 3D height map. You don't have to scan it several times. It's directly in one scan.
And to describe the intensity image, maybe not everybody understand what we mean with that. It's like the monochrome line scan camera image. So we have a, yeah, it's a monochrome image what we generate, and it's just yeah, it's directly with the point cloud. So you can do an overlap so that you see both, or you can look at them also separately.
Okay. What is the accuracy for weld seam inspection? Or what accuracy is necessary, I guess?
So it depends on which part, but most of the time we do it with the Tensor 2520, and this one has X accuracy around 50 mu in X.
Okay. Somebody's asking if we'll share the PowerPoint. I was not planning on that. However, if you registered for this webinar, you will get around 2 hours after this webinar, you will get a link so you can rewatch it. But if you have a project and you want more details, reach out to us. You can find our contact details on lmi3d.com. And we're happy to talk and discuss details with you. Somebody is asking, for example, with the Gocator 2500, you're showing a linear motions during the image acquisition. Does LMI provide any integrated motion systems, either with the product or with a starter kit?
Well, we don't provide that directly, but we, for instance, it was now a few 2 months ago, I was talking to B&R, which are also known for their tracking system or for their conveyor system. So we don't have our own system for that, but we do have partners, of course, or on the market there are several which we know, and they also know us. So there is I would say, for the movement, it's pretty easy. You just need an encoder signal to get it synchronized and to know, okay, where it is. But for a full solution, as I said, B&R is one of our partners as well.
Okay, the next question is, what's the maximum transport speed to measure 0.1 millimeters?
It depends if you mean in X, Y, or Z, but 0.1 millimeter for our sensor is not critical, I would say. So
yeah,
you can go fast, but we need to know more if you are speaking about X, Y resolution or Z resolution.
Exactly.
Okay.
It's kind of hard to say, but just we have scan rates with the LCI, for instance, or also with the other sensors. It can goes up to we can reach to 10 kilohertz or 15 kilohertz. So that means if you go the easiest to calculate easier 10 kilohertz, that means you have 10,000 profiles in a second. So that's one number what we provide. 0.1 is the accuracy if you need, and then we know actually how fast you can go maximum.
Okay. Can you measure overhang of electrodes or electrode angles?
What's the overhang? I don't understand the question.
Overhang is like more than you need. I'd say that's what's meant. Like.
Well, so if it's in the stacking process, or maybe you can rewrite the question. That would be great. I don't know what to answer right now in what situation it is.
But
it's kind of hard.
I mean, we can still isolate the electrode with surface blob, and then we have for the angle surface plane. So once all our electrodes are isolated, we just need to put a surface plane on it to get the angle on all directions. And for overhang, I guess if we put a simple bounding box, we will get the size of it, and if it's overhanging, then it will be too big and won't match the tolerances, the dimension we need.
Okay, so Paul, I hope this answers your question. If not, just leave us another message and we'll go into more detail. The next question is, do you always require encoder signals to collect 3D point cloud with laser triangulation and motion systems? Or are you able to use other position protocols?
We can use an encoder, but you can also work with speed. So if you have a constant speed, you can give the speed to the Gocator, and it will be able to make the calculation and generate your point cloud. You can also send a trigger, a hardware trigger, to the Gocator, or software trigger via the protocol I mentioned before, Modbus, Ethernet IP, Profinet, or TCP. But just to start the sensor. Then you will need, if you are working in surface mode, to give the speed or to get to have an encoder signal.
Great. So Paul just replied with, thank you. The overhang is often seen as the jelly roll goes into the can.
Oh, so you're talking about the cylindric cells, I guess, the jelly roll.
Yeah.
And this goes into the can. And the overhang means now over the top, so before the closure. But this, if that's what you mean, well, it's a simple, I would say, height measurement actually, or it's overhanging over the
on the side.
On the side. Then it depends how we have to adjust the scanners. So either from the, if you scan from the side and from the top, well, you get the 180-degree image. You can use several tools to measure the overhang, or to either to measure or detect if there is an overhang. So before proceeding with the next process.
Okay. I remember there were a few more questions. Unfortunately, I got kicked out in between. So some of the questions are gone for me. If you guys can one of you could take a look at the chat and just at the bottom. I remember one that was asking if we were already working with other battery manufacturers. So if we're already, have our sensors installed in some battery applications. I'm pretty sure you guys can probably not tell us any names, but
yeah, but we do. That's that's the reason we show those examples. What we show, they are real. So we do work, either we work on them or we already realized those. So our sensors are already mounted in several machines at battery manufacturers, of course, definitely. We are actually in China. We are also very actually number one in the 3D inspection regarding the battery industry.
Okay, great. So somebody's asking, what applications have you solved before regarding other electric components?
Well, besides the batteries, there are, of course, other options. For instance, a simple application where if the battery is or the battery pack is ready, you have to connect it somehow. This is also automatic process where a robot usually takes the plug and plug it in, and it has to plug properly inside. We simply scan this area after this assembly and check. That's an easy application. Measure the height. The height or the coplanarity as well of those plugs. That's just one example, but there are even more. One of those in what you see here in the picture still is the cooler inspection.
Okay. Did I miss any questions?
No, I think no.
Okay. If I did miss your question, please type it in again. Sorry about that. In the meantime, I have one more question. Somebody's also asking, what about cylindric cells? Can you also inspect those? Because we more talked about the battery packs.
Yeah, exactly. We were concentrating right now in this presentation more on the prismatic cells. Cylindric cells, there are similar applications in the beginning, but also, well, there are some, for instance, they don't have stacking. You roll usually the electrodes and the insulator, but there are also applications where you have to check for defects. So if you have and usually if the cap is coming on, there are also welds which we're inspecting. So yes, definitely, that's actually the way, or what I see. It's a moving from prismatic cells to cylindric cells.
Okay. And there's somebody else asking about our multi-sensor setups. How does that exactly work? I guess we just really briefly only mentioned that.
Yes, so if we want to get a 360 point cloud or even 180 degrees point cloud, then we can have a multi-sensor setup, so mounting all our sensors around the part we want to scan. And then it's very easy to directly align all the sensors. One of the sensors is the master, the other sensor are the body, and all the body will send their point cloud to the master, so that at the end you only communicated with the main sensor and you get directly the point cloud from one sensor. You don't have to reconstruct your point cloud after that with a PC or with an external software. It's much easier for analyzing it.
Okay, great. So many great questions. So, if there are no other questions, then all there is for me to say is thank you for joining. I hope you learned something today. If you want to know more about LMI, visit our website at lmi3d.com and reach out to us if you have questions or a project. And we are happy to help you.
Yeah, thank you very much.
Thank you.
Thanks.
Have a good day. Take care. Bye.
Bye.
Bye.